In recent years, transformer-based large language models, or LLMs, have transformed the field of natural language processing by enabling advanced tasks that involve understanding and generating text based on context. This innovation has extended to requirements engineering, a key area in software development where clear and accurate specifications are essential. Researchers Wad Al-Hashan from Imam Muhammad ibn Saud Islamic University in Saudi Arabia, Alessio Ferrari from University College Dublin in Ireland, and Liping Zhao from the University of Manchester in the United Kingdom, conducted a study titled, "How Effective Are Generative Large Language Models in Performing Requirements Classification?" The study begins by highlighting the context. Generative LLMs, which can create new text outputs, have opened up new possibilities in various applications. In requirements engineering, these models have been tested for tasks like detecting trace links between requirements or ensuring regulatory compliance. However, one specific task, requirements classification, has seen limited use of generative models so far. Requirements classification involves categorizing software requirements into types, such as functional or non-functional, or even more specific classes like security-related ones. Traditionally, non-generative LLMs, like BERT, have performed well in this area because they excel at understanding and analyzing text without generating new content. The problem addressed in this paper is the lack of exploration into how generative LLMs handle this classification task. These models, which produce context-aware outputs, might offer unique advantages, but their effectiveness remains unclear. To investigate this, the researchers designed a comprehensive experimental study. They focused on three popular generative LLMs, Bloom, Gemma, and Llama. These models were tested on both binary classification, where requirements are sorted into two categories, and multi-class classification, which involves multiple categories. The experiments involved over 400 trials across three widely used datasets. Promise NFR, which deals with non-functional requirements, functional quality, which distinguishes between functional and quality attributes, and SecRec, focused on security requirements. The study examined four core components that could influence performance: the models themselves, the datasets used, the prompts given to the models, and the types of classification tasks. Prompts are the instructions or questions fed to the LLMs to guide their responses, and the researchers experimented with different formulations to see what worked best. In terms of results, the choice of model made a significant difference. Bloom stood out for its precision, reaching a maximum weighted precision score of about 0.77. This means Bloom was particularly good at correctly identifying true positives without many false positives, which is crucial for avoiding misclassifications. Gemma, on the other hand, excelled in binary classification tasks, especially in recall, with an average weighted recall rate of 0.51. Recall measures how well the model identifies all relevant instances, so Gemma was effective at catching most of the correct classifications in simpler binary scenarios. Llama provided a more balanced performance, doing well in both precision and recall across binary and multi-class tasks. This balance makes Llama versatile for different classification needs. The researchers also found that prompt design was critical. Assertion-based prompts, which directly state what the model should do, like, classify this requirement as functional or non-functional, proved to be the most effective, outperforming other styles. Another key observation was the robustness of generative models to dataset variations. Even when the input text changed between datasets, the models maintained consistent performance, suggesting they can handle diverse data sources reliably. To put this into perspective, the study compared these generative LLMs with top non-generative models from previous research, such as Llama-in and SBERT. In multi-class classification, the generative models generally underperformed compared to these non-generative ones. For instance, Llama-in showed superior results in more complex multi-class scenarios. However, in binary classification, the performance was mixed, with non-generative models like Llama-in often coming out ahead. The contributions of this paper are significant. It represents the first thorough experimental study dedicated to evaluating generative LLMs specifically for requirements classification. By analyzing the four core components, models, datasets, prompts, and tasks, The researchers provide valuable insights into the strengths and limitations of these models. For example, they emphasize that factors like prompt design and the underlying architecture of the LLMs are universally important for achieving good results. On the other hand, variations in datasets have a more situational impact, depending on the complexity of the task. This means that for simpler classifications, dataset differences might not matter as much, but for more intricate ones, they could play a bigger role. Overall, the study guides future developments in this area. Researchers and practitioners can focus on optimizing prompt structures to enhance performance and select model architectures that align with specific task requirements. This could lead to better tools for requirements engineering, making software development more efficient and accurate. By understanding these dynamics, the field can continue to evolve, leveraging the power of generative LLMs while addressing their shortcomings.